Hi, welcome back to my classes on advanced organic chemistry. So previously I did 4 classes on advanced organic chemistry. Before that, many classes I took on basic organic chemistry. So this is aromatic electrophilic substitution reaction. So before coming to this particular video class, just go to my YouTube channel Play Store in organic chemistry series, class number 6. It something about substitution reaction. That one, if you watch and then come to this one, it will be more easy for you to understand the concept, or it will be very easy. So there I explained that the chemical reactions, organic reactions are of different types, like substitution reactions, addition reactions, elimination reactions, rearrangement reactions. So among that, substitution are of 3 types: nucleophilic substitution reaction, electrophilic substitution reaction, and free radical substitution reaction. So in electrophilic substitution reaction, some of the basics required for this particular video class is explained in detail. Anyhow, most of the topic related to advanced organic chemistry of aromatic electrophilic substitution reaction will be explained in this video also. Now, this is just a comparison for cyclohexene when it reacts with bromine, and benzene reacts with bromine. The difference between cyclohexene and benzene, that cyclohexene contains one double bond in a cyclic hexagonal shape organic compound, whereas benzene, it is also hexagonal type compound, but having 3 double bonds, that is conjugated double bonds. Okay, to see the difference, cyclohexene, so this is the structure of cyclohexene when it reacts with the bromine. Okay, so bromine molecule, the double bond, because the double bond it is type of alkene. Alkene can attack bromine because bromine is more electron. It can attract the electron density. Then this electron shift, possible shift, it is there. So we'll be getting bridged structure. Okay, so here it represents that both the bonds are towards us, and bromine, it is not on the plane of that molecule, it is towards us. And then the other bromine, it becomes bromine Br negative, because the bond homolytically it cleaved, heterolytically it cleaved. That means both the electrons are bound to the bromine. That means it is one of the bromine, it becomes Br minus. Okay, so now the Br minus, it can also attack this particular compound, because it is a bridge structure. Bridge structures are not always stable. So now this Br minus can attack from the backside of this plane of this molecule, and backside of attack finally results in the particular compound, which is trans 1,2-dibromocyclohexane. Okay, so here this particular bromine is away from us. This particular bromine is towards us or near to us. Okay, so this is about cyclohexane. If it is benzene, so benzene, we know it consists of 3 double bonds, and when it reacts with the same Br, but it needs help, because we know already that bromine, the recombination reaction of benzene, it needs a catalyst. FeBrg can take as a catalyst, so that the bond cleavage takes place, polarization takes place. The bromine-bromine bond undergo polarization in presence of FeBrg. Then the first Br, which is written here, it will be positively charged, so that the electron density will go there. Okay, and we'll be getting we're supposed to get a product like this. If you compare with that of cyclohexane, but actually this product is not obtained in practical. Okay, that means the double bond present in benzene or such type of compounds are not a double bond as such. They show a property known as the aromatic property. Okay, so aromatic compounds, even though it contains a double bond, we cannot treat it as a normal alkene. You have to treat a separate category of molecule, which we call as aromatic compounds. So aromatic compounds, say benzene, when it reacts with bromine in presence of ferric bromide, it gives bromobenzene. Okay, so we'll be getting bromobenzene. It is actually a substitution reaction, not the addition reaction given by the alkenes. Okay, so here one of the hydrogen present in this particular position, it is replaced by Br, and the side products will be HBr as well as FeBr3. Will get it back. Okay, so in electrophilic substitution, in my previous video, that is on the basic or the organic chemistry class series, I explained about this, about the formation of the mechanism of electrophilic attack of on benzene. Okay, there I explained that it consists of three steps, like formation of electrophile, attack of electrophile, and deprotonation to give the final product. Okay, there is no variation from that. It is correct only, but here I'm going in a different way. I'll explain in a different way to explain that. I'm not going in detail about the formation of electrophiles, how the electrophiles are formed for different type of reaction like halogenation, nitration, sulfonation, FeBrg alkylation, FeBrg acylation reaction, how these electrophiles are formed. That is in detail explained there with the formation of bonds, breaking of bond. That is very much important because we should know what type of, how these electrophiles are formed. When electrophile is formed, then only it can attack benzene. As such, we cannot supply electrophile for a reaction. We'll be adding some chemical. We'll be adding the required chemicals, which will in turn convert into the electrophile, and that electrophile attack the aromatic compound. Attack of electrophile, then finally deprotonation, removal of H plus, and give the final product, aromatic substituted product. So here I'm going in a different way, that is Arenium ion mechanism, or we call it as Wieland intermediate mechanism for formation of a sigma complex. It is the same at what we see in there, but in a different way we are explaining it. That is, we call it as Arenium ion mechanism. Okay, in Arenium ion mechanism, there are two steps. So we can call it as a two-step mechanism. Okay, the first step, that is formation of the Arenium ion, which is also called as Wieland intermediate or even sigma complex. Okay, so it is the same. Okay, here I am just representing benzene ring. Benzene ring, one of the carbons, one hydrogen also I am representing here. Okay, so this is benzene ring. All the carbon atoms are having hydrogen, but only one hydrogen I'm indicating here to understand or to realize this mechanism properly. And when an electrophile comes, how the electrophiles are formed, that is, you have to watch my previous video on organic chemistry, basic organic chemistry. When electrophile comes, one of the double bond, okay, when we cannot treat as a fully double bond, it is a partial double bond character because it is in delocalized state. Okay, anyhow, it attacks that electrophile. Suppose that this electron density attacks the electrophile through the carbon in which the hydrogen is attached. Okay, all are having equal probability, but only for our convenience, I'm saying that this electrons, it goes through this carbon and attacks the electrophile. Only the electrons can move, the positive charge cannot move. Therefore, the movement of electrons, it is represented here. Okay, and it is a slow process. We'll be getting the Arenium ion. Okay, so this is the Arenium ion formation. Okay, so the electrophile, it attacked. Okay, so electrophile attacked there. We got electrophile attached there. When electrophile attached there, this double bond actually it broke in such a way both the electrons gone to this carbon, then it will give one electron to the electrophile. That means this particular carbon, which I indicated with the arrowhead, that carbon, it is getting positive charge. Positive charge means charge separation, that is less stable. Whenever a positive charge is there, that positive charge is on the 2p orbital, the p orbital or the p orbital of the carbon, and there are parallelly a p orbital is there with the electron. Therefore, this electron or pi electron can move there to stabilize this positive charge. We call it as resonance stabilization. Okay, so resonating structures are possible. That's why I put it in square bracket. So the resonating structures I'm drawing. So here we will be getting a double bond now. Okay, a new double bond is formed at this site. It's the same molecule only. This is not a different molecule. Same molecule structure, rewriting it. Okay, the possible electron movement. Then here this position will be getting a positive charge. That means the positive charge is delocalized, or the electrons are delocalized. I cannot say that positive charge is delocalized as such. Electrons are delocalized, therefore the charge shift to the next carbon. Then again, there are pi electrons. The next pi electrons or the p orbitals, the electrons, it will share or delocalize such a way that a positive charge is formed at that particular position represented here. Okay, represented here. That means the positive charge is on this particular carbon, it can go to the next positive charge, and here also on another carbon. That means the positive charge, it can even go back. That's why the arrowhead represents this movement. Electron movement can go back and repeat. So these mainly these three structures will be shifting. Okay, this possible arrangement of electrons in that possible arrangement of the pi electrons, it will be shifting to and fro, so that the benzene ring will not feel the effect of positive charge as full positive charge, even though the positive charge is there. Therefore, it can represent it as all the three combination combined, or we call it as the resonance hybrid in our way. This is nothing but the Arenium ion. So the aromatic electrophilic substitution reactions follows Arenium ion mechanism, in which the first step itself is the formation of Arenium ion. Now, the Arenium ion here I represented with benzene, therefore we can call it as a benzenium ion. If other than benzene, if any other aromatic compound is there, generally we call it as Arenium ion. Here it is benzene, therefore benzenium ion is formed. Now this sigma complex, it is stabilized by resonance. That means the positive charge, it is dispersed on so-called the ortho and para position. What is ortho and para position, you already know, but anyhow, coming in this particular video class only, in detail I'm explaining about that ortho para position, because aromatic electrophilic substitution reaction, the ortho para directing groups, ortho para ratio, as well as meta position substitution, all have very important. Therefore, with a positive charge dispersed on ortho and para position to the site of attachment of the electrophile. That means the sigma complex, it is stabilized by the resonance. This step is accompanied by the loss of aromaticity. That means it loses aromatic nature. We know what is a requirement of an aromatic, the 4n+2 pi electron rule, that pi electrons are not there, pi electrons are removed from that. Therefore, we can say that its total aromaticity it got disturbed. And we know that when aromaticity is there, aromatic nature is there, they are more stable. That means this particular benzenium ion is at a higher energy level. They are less stable. Okay, comparatively, we can say compared to benzene, benzenium ion is less stable. Less stable when we say, that means higher energy. It is having higher energy, or to form this benzenium ion, we need to supply more energy. Activation energy is required. Activation of energy of activation is high. It is also the slow step, or we can call it as the slow rate determining step. And in the rate determining step, we can see the benzene molecule is there, the electrophile is also there, both are there, two molecules are there. Therefore, we can say that it is bimolecular, or in another way we call it as it is a second order reaction. So the formation of the aromatic electrophilic substitution reactions are second order reaction, because in the slow rate determining step, we have two molecules, the substrate molecule, which is our benzene for the aromatic molecule, as well as the electrophile is also present. Now, in the second step, the leaving group departs, leads to the regeneration of aromatic stabilization. That in our previous video class, related to this, we said that deprotonation. Deprotonation means minus H plus. Okay, so the same thing, deprotonation, which is a fast step, because the molecule want to regain its aromatic nature. Okay, so if H goes as H plus, then this electron H goes as H plus means these two electrons, the bonded electrons will remain back. Then it will go to the benzene ring and gets the aromatic nature. So this is the Arenium ion mechanism. Now, if the electrophilic species is not an ion, so here we just seen that it is E plus, represented the electrophile as E plus. That means it is an ion. Okay, if the electrophilic species is not an ion, but a molecule with a polarized covalent bond, the mechanism can be represented as, okay, so this is the benzene ring with a hydrogen is represented there. Okay, then we are taking the Ez, that means it's a molecule. Okay, it's a polarized molecule. That means these two are having difference in electronegativity, such a way that this particular atom E, it can become electrophile, and Z will go as a Z minus. Then further it will combine with the H plus present in that. Okay, therefore, this mechanism we can represent as formation of Arenium ion, but the electrophile, the counterpart still it remains there. Then that will go out. Then that counterpart is Z minus will move away. Further deprotonation takes place, or the molecule gains its aromatic nature and will get the final product. Now, moving on to the energy profile diagrams, what will be the energy? What are the different stages of this Arenium ion mechanism, and what are the different energy states of that? Okay, so that energy profile diagram, I'm just drawing the energy levels to get a better understanding. So first energy level, then a very high energy level. Why high energy level means less stable. Then comparatively stable energy level. Then again it goes to a little higher energy level, less stable state. Then finally goes to a very stable state. That means the reactants, when it want to give a product, the energy difference you can see, the energy difference should be less, should be more stable product will be formed, or which is having lower in energy. Now the starting material, that is our benzene molecule, or the aromatic molecule, its energy is represented with this scale, with this level which is present there, and it combines, so it reacts with the electrophile plus E, that is E with a positive charge, what I mean here. Okay, then it forms a less stable transition state. Okay, so this is a less stable transition state. That means the benzene molecule, even it completely didn't form bond with the electrophile. A partial bond is formed and a partial double bond shifting takes place. That is the least stable state, least stable energy state. We can call it as a transition state. Immediately it will convert into a little more stable state. That is the Arenium ion. Okay, now this Arenium ion state, even it is possible for us to separate it. That I will be explaining in the next class. In this class, I will continue with this. Okay, so even this stable, this state is somewhat even stable state. If there are enough substituents present on this benzene ring, then we can separate this molecule out with the positive charge on that Arenium ion. It can be separated. Then this state further gives a little more higher energy state or lesser stable state, in which the deprotonation initiated. So that means this CH bond breaks slowly. Okay, the remaining structure as such. Okay, so the CH bond breaks slowly. That is, removal of proton takes place. That bond breaking, it is a little bit less stable state than this particular stable state. Then it gives the final product as the electrophile substituted benzene molecule. Okay, so this can be taken as the energy profile diagram. Usually, when we draw energy profile diagram, we take free energy in y-axis and reaction coordinate in x-axis, and the same can be represented like this. So you can see the difference in energy. Okay, so the first state, that is the reactants energy level to the first transition state energy difference, it is represented here. I'm not giving any value here. Okay, so again the difference between the first transition to somewhat stable transition, that is Arenium ion. Then again the energy difference between the Arenium ion to the second transition state, or you can say third transition state, and there is an energy difference. By even by mistake also should not draw that equal levels, should not draw. This is somewhat lower energy level than that of the first transition state. That's why I have separated here to identify that. Okay, then the third one, the last one, the energy difference, as well as you can see from the final product to the substrate or the reagents, benzene as well as the reagent electrophile, there is also energy difference is there. The final product is having the lowest energy, or that is the most stable form compared to the starting material. That's why they undergo reaction. Otherwise, there is no reaction possible if the final product is not stable than the substrate or the reagent. Okay, so that is the most stable state, the next stable state, and the Arenium ion, that is the least stable state. Okay, all these three products can be separated with proper methods that I will be explaining in next class. So you have to wait for that class. I'll continue with this energy profile diagram and further explanation of some substituent effects and okay, so here the reactivity in substituted aromatics, how, what will be the reaction ratio, or what will be fastness of the reaction, and what are the substituted the substitution, the different groups which are substituted on the aromatic compound, how they affect the reactivity, that is explained here. The substituent groups on a benzene ring affect the electrophilic aromatic substitution reaction mainly in two ways. That is, it will affect the reactivity as well as it will affect the orientation. Okay, so reactivity, we can say if it is activated, it will undergo faster reaction than benzene. If it is deactivated, it undergoes slower reaction than benzene. Then it may be ortho-para orienting group, or it may be meta orienting group, or meta directing, or ortho-para directing group. So all these discussed in the next coming slides. So you have to keep in mind that I cannot separately, cannot say the reactivity and orientation or explain together. You can take it out whether if it is activating, whether it will be ortho-para directing, or deactivating will be meta directing, or such a thing. So it will be different for different substituents. Explanation is there. Now the reactivity in substitute aromatic with the electron donating groups. If the substituent is an electron donating group, or it releases electron to the aromatic ring. Okay, I'm taking benzene as example. As a benzene I took as example with the substituent and the substituted group. Okay, I didn't write any group here. Only a sphere is written there, given there. Okay, so that is having a lone pair of electron. It's an atom or group of atom, but it is having lone pair of electrons, or it is able to donate electron or able to release electrons. In order to understand, understand easily, I put a lone pair of electrons so that this electron it can donate. Okay, now this one you can call it as an electron donating group, EDG, and we know that the electron donating group, it will create a negative charge, a partial negative charge in ortho position. We have two ortho positions. Okay, a partial negative charge is on ortho position and even at a para position. So this one also explained in my basic or organic chemistry class. Please go through there how the electron movement. I am not drawing that electron movement, and that will be a wastage of time. You already studied in even in pre-university level also that there is a possible resonance stabilization, and this ortho and para position will have higher electron density, and we are explaining about electrophilic substitution reaction. So electrophilic means it is having electron deficiency. Okay, and these are the different positions in the benzene ring when a substituent is present. The position, the group which is attached to the benzene ring, that particular carbon we give number 1. Then either we can go right side direction movement, or can count in the left side. Okay, so here there are no other substituent present, therefore we can count on either ways. Okay, if any other substituent present, then the counting should go in that particular direction, so that the substituent should get the least preferable numbers, or least number should be given to the substituents taken together. Okay, that will explain in other class. I think already I explained in one of my video class how to count the number, give the substituent numbers and okay, so this is the number as well as the name for the different positions, ortho and para position, and position 3, position 5 we call it as meta position. Therefore electrophilic substitution reaction, electrophile, when an electrophile comes, it loves the negative charged centers. Okay, or it is attracted towards the negatively charged centers. It is positive charge, only the negative charge centers can attract it, or it will be taken, withdrawn, it will be attracted. Even this representation is wrong. Arrowhead, if you show this side, it will be even better one. That means this particular site, the electron can take this electrophile, or this particular position, we having the electron density, more electron density, it can take this electrophile. Okay, or even the para position, that electron density can attract that electrophile. Okay, so when you write a note, it better you give the arrowhead in a reverse case. You start from here and give an arrowhead here, because that is the better representation. Electrons will attract always. That is the concept that we need to follow. Then it is easy to understand the organic chemistry. Okay, so the electron density of the ring increases. That we've seen already, that ortho position and para position having more electron density, charge separation, negative charge is there, which results in activation of the ring towards electrophilic substitution. That means more electron density came so that it can attract an electrophile faster than a normally unsubstituted aromatic compound. That is means if an electron donating group is there on benzene, it will be giving electrophilic substitution reaction at a faster rate than that of benzene. Okay, now the resulting resonance form of the Arenium ion favors the substitution of the second group at the orthopara positions, that is position 2, which is equivalent to position 6, as well as position 4 relative to the original group, which is already substituted and present in the benzene ring. Now, the free energy of activation will decrease as resulting transition state enjoys additional stabilization due to a more delocalized Arenium ion. So this I can represent with a schematic representation. So again, I'm taking the same diagram, but an electrophile it is attached. Okay, so electrophilic substitution already, electrophile not substituted as such. Electrophile got attacked, or electrophile is attracted towards the benzene ring or substituted benzene ring, and the substituted group, it is electron withdrawing group, and we know that then it will gives a positive charge to the next carbon atom present. So here a double bond was there like this. The double bond it given electron density to the electrophile and forms a bond there. Therefore, the next carbon it loses an electron density. Therefore, it gets a positive charge. Whenever it gets a positive charge, then the next 5 electron it will start weakening. Okay, so that pi electron starts moving towards it will start giving electron towards that positive charge center. Okay, so that is represented here with that dotted line, and that positive charge diminishes, it becomes partial positive charge. It was full positive charge, but one little bit of electron density reached there because of the conjugation present there, or because of the support given by the pi electron present in the next carbon atom, because that pi electron as well as the positive charge center were in the same energy, same plane of the molecule. Therefore, the sharing of electron is possible. Therefore, it becomes partial positive charge. When what about the next carbon atom? So this carbon atom will share the positive charge. Okay, therefore we can say that the full positive charge now it is shared by 2 carbon atom as partial positive charge. So when there is a partial positive charge here, then this pi electron will try to donate. Okay, so it will weaken, it will give the electron density towards that one because it want to neutralize the charge. Therefore, you can say that now the partial positive charge, it will be distributed and become partial positive charge. Further, positive charge is reduced, become partial positive charge, and it got distributed to another carbon. The positive charge got distributed to another carbon. Now, this much it is there for benzene ring also. Okay. Now, in addition to that, so that is given here additional stabilization. Okay, so what I represent here, this much it is there for even benzene ring also. If we take this possibility, can explain. Now here one additional stabilization is present, or delocalization is present, because a lone pair of electron is there. Or this group, it is an electron donating group. It will donate electron to this positive charge, or throughout this positive charge. If it gives an electron here, then that electron can move throughout this shared p orbitals. Therefore, you can say that electron donating effect, it is represented there. The lone pair of electron gives near to the carbon with that partial positive charge. Then it forms a partial double bond nature first, or later it becomes a full double bond, then breaks and becomes partial double bonds. Okay, then we can say that the first carbon which had a full positive charge, now it become partial positive charge, and it got distributed to the next alternate carbon as partial positive charge, and again a partial positive charge reached to the electron donating group. That means a more additional stabilization or delocalization takes place, and a more stabilized Arenium ion is obtained when there is an electron donating group present, when we compare with that of a benzene ring. Okay, now therefore the reaction rate is increased relatively to the rate of an unsubstituted aromatic ring, because it is more stable, therefore faster reaction takes place. Now the activation of ring by substituent can arise due to the resonance effect as well as inductive effect. Till now what we seen, that is the resonance effect. Inductive effect also we see. First we again see the resonance effect. This is the resonance effect in which the substituent or the electron donating group has got a lone pair of electron, or it got extra electron density present in that, which it can give. Therefore, either if it is having a negative charge, even if it is having negative charge, if it is an oxygen with a negative charge, then the negative charge also it can give. Therefore, the resonance effect is seen in case of substituent having lone pair of electrons, or having negative charge, or even having extended conjugation. If this particular group has got a another carbon-carbon double bond present here with the conjugation, that means alternate double bond present, alternate single and double bond present, that we call as the extended conjugation, then it will give a resonance stabilization of that Arenium ion. So examples of such groups are NH2 group, NHR group, that is amine group, primary amine group, secondary amine group, amide group, NHCOR group, hydroxyl group, alkoxy group, vinyl group, phenyl group. These are all the different groups which can activate the ring by resonance stabilization. Even inductive effect means a group electron donating group is there, but it is not having a lone pair of electron, but still its electron density is such a way that it will give electron towards the benzene ring or the carbon which is present in the benzene. So then further we know that it travels through the sigma bond. The inductive effect travels through the sigma bond. It is a bond, it is a permanent effect whereby the electron density is moved through the covalent bond when two atoms are having difference in electronegativity. Okay, that you already studied. Okay, therefore inductive effect is seen in the case of alkyl substituents, say methyl substituent or ethyl substituents. They can give this type of inductive effect. That therefore it is as such, it is not affecting that resonance or the pi electron movement, but the electron density is increased here, which will support this movement of pi electron or the Arenium ion stabilization. Therefore, if you see the energy level to the reaction coordinate, the graph, if you see the energy profile diagram, I'm taking benzene as example, as well as toluene or methyl substituted benzene, CS3, C6H5CH3, so we call it as toluene. And it is reacted with NO2, that is nitration reaction, in which NO2 plus, which positive charge is there on nitrogen. Okay, so here it is written small letters. I think you can see this, it is visible to you. Okay, so a benzene or a toluene molecule is taken, then it is added to, it is reacted with NO2 plus, or it is nitration reaction. Okay, benzene or toluene separately hurt finger. It is not a mixture of all these three. If it is benzene, so the energy level it is represented. Okay, so if it is benzene, the nitration of benzene, finally initially it undergoes the first transition. First transition already I explained in the energy profile diagram. I'm not giving the structure here. Then it becomes somewhat stable Arenium ion state. Okay, so this is the Arenium ion state, benzene ring, NO2 group attached, and a positive charge, it is delocalized, that is Arenium ion, a little bit stabilized state. This is not the final product as such, the transition state only. Okay, if it is toluene, then we can see the energy level. energy level, it is little bit lower energy level. Lower energy level means a little bit more stable, what I mean to say. Okay, so that is the NO2 substituent present. Again, it is an Arenium ion only. You can see whether it is a ortho position or meta position or para position. I'm not here telling now. It is a meta position actually. Okay, so I said I am not telling, and I said it. Okay, so again, the other possibility. Again, it gives the even further lower energy level. That is the ortho position substituted Arenium ion, as well as the para position substituted Arenium ion. So that is the meta position. These two are the ortho and para position substituted Arenium ion. That is a transition state only till we not reached to the final product. So you can compare this, compared to benzene ring, how the CH3 group or electron activating, sorry, a ring activating group decreases the energy level of the transition state, or how fast the reaction can take place. If the transition state energy level is less, then even more faster will be the reaction, faster will be the formation of the transition state, and suddenly it gives the final product. Now, reactivity in substituted aromatic with electron withdrawing groups. Okay, so electron withdrawing groups, if a substituent group withdraws electron from the aromatic ring, okay, electron withdrawing group represented with the arrowhead. Oh, I think electron donating group I could have represented with the arrow down head. Okay, now anyhow, that completed. So here it represents that the group, it takes electron away from the benzene ring or from the aromatic ring. So that is electron withdrawing group. Therefore, it gives a partial positive charge to the ortho position and partial positive charge to the para position. Again, this electron withdrawing group's resonance effect, it is explained in the previous video. I'm repeatedly telling that video. Okay, now I'm repeatedly telling that video. I'm also request you to subscribe. Those who are yet not subscribed, all my regular students, all are subscribed my YouTube channel and supporting. Those new to this YouTube channel, my intuition. Myself, Dr. Prasad Puthiyillam, I request you to subscribe this YouTube channel, like the videos, and share it to others. If you understood the concept, please share it to others so that everyone can understand this. Because nowadays it is online class, importance of online class, and as well as the difficulties of online class, everyone knows. Okay, so please do subscribe my YouTube channel and support me. Okay, so here it is electron withdrawing group. Electron withdrawing group, then the positions I'm representing 1, 2, 3, 4, 5, and 6. These are the 6 positions compared to the electron withdrawing, that compared to the substituent present there. And when it comes case of electrophile, now the ortho and para position, they are also having positive charge. Electrophile is also having positive charge. They will repel each other. Okay, so there is no possibility of substitution at a ortho and para position in this particular case. Okay, therefore only 3 or 5 both are equivalent positions. Okay, since I counted it in the right side direction, it become 3 and the other one is 5. Or we can interchange the positions 3 and 5. They are same, having same electron density. Okay, compared to ortho and para position, if you force this molecule to undergo reaction with electrophile, only the possibility is that 3 as well as 5 can attract the electron. Okay, so the position 3 takes the electrophile, or position 5 takes the electrophile. Okay, or it attacks meta positions. That means the electron density of the ring decreases, leading to the deactivation of the ring. Energy of the transition state thereby increases and leads to the formation of less stable delocalized Arenium ion. The resulting resonant form of the Arenium ion favors substitution of the second group. That means second another atom or group of atom, which we call as the electrophile as such, the coming atom or group of atom. It is directed towards the meta position, that is position 3, which is equivalent to position 5 relative to the original group. Okay, deactivation of aryl ring can also be attributed to resonance as well as inductive effects, similar to that of activation of the aryl ring or benzene ring. Okay, aryl, whenever we call it as aryl, immediately benzene name will come to our mind. Benzene only is an example for aryl group or aryl aromatic compounds. Almost all aromatic compounds. It is easy to understand the concept with benzene, and then we can go to the higher aromatic compounds. Okay, so the examples like aldehyde functional group, COR functional group, carboxylic acid functional group, ester functional group, NH3 plus. Okay, so that is a quaternary amine group. Okay, so if positive charge is there, therefore positive charge is there means it will attract the electron. For NR3, trialkyl substituted nitrogen with a positive charge. CF3, that is fluorine, C triple bond and cyanide, nitro group, SO3H, sulfonic acid group, all are having deactivation of the aryl ring or benzene ring. Say example, if I take that of aldehyde, how this it attracts or it withdraws the electrons. Okay, it is connected to the aromatic molecule. AR represents aromatic, or you can take it as a benzene ring there. The C double bond. Okay, so the C double bond, it will shift the electron because oxygen is more electronegative than that of carbon. The possible electron shift and it takes electron from the aromatic. You can see that from aromatic the electrons are moving towards the aldehyde functional group. Therefore, we can say the aldehyde functional group or the carbonyl group present. Okay, carbonyl group is present in aldehyde, it is present in ketone, present in acid, it present in ester. Okay, so we can say that all these are electron withdrawing. Even similar type of arrangement is there in case of NO2 as well as SO3. They are in place of carbon. We have nitrogen as well as sulfur. It is nitrogen double bond with oxygen, then one single bond with oxygen. Here also sulfur double bond with oxygen. So same type of arrangement it can expect. Okay, whereas if it is CF3, then here it is the fluorine. Okay, three fluorine atoms are there. Fluorine is the smallest atom. It is highly electronegative compared to carbon. Therefore, we can expect an electron movement inductive effect towards the fluorine. We can say that fluorine is a negative inductive affecting group. It takes the electron density towards it. Okay, or it takes the electron density away from the carbon. Then that's why we call it as negative. It takes away, therefore we call it as negative inductive affecting group. And finally, at aromatic carbon to this CF3 carbon, there is a electron density movement away from the benzene ring, or it deactivates the benzene ring. Therefore, if you see the energy profile diagram, benzene as well as nitrobenzene, I'm taking the example, either benzene or nitrobenzene, when further reacts with an electrophile, not given the example as such, just electrophile, simply E plus. So I think you can see here E plus it is written. So the energy level it is represented there. So benzene, it reacts with electrophile. We know it forms an somewhat stable Arenium ion transition state it reaches. Okay, and if it is NO2 group, okay, it increased. Okay, NO2 group at electrophile at the meta position, it increased. Even if it is further it increased to a higher energy level if it is at the ortho as well as para position. Therefore, a reverse case it is observed here. Okay, so if it is electron deactivating group, electron withdrawing group, or aromatic ring deactivating group, we can see how the name came, deactivation. That means it deactivates the ring towards the electrophilic substitution reaction, or we need a higher energy to pass this transition state. Comparatively, meta is a little bit lower energy level, and ortho and para having very high energy level. Therefore, the expected product after if the aromatic ring having a deactivating group is always a meta substituted product, which is somewhat a more stable transition state compared to ortho and para. And even when we compare with that of benzene, they are even less reactive. Now, reactivity in substitute aromatic with halogen as a substituent. Okay, halogen we know that is fluorine, bromine, chlorine, bromine, iodine. Okay, we treat those as halogens. Halogens provide a peculiar effect when attached to an aromatic nucleus. So benzene ring halogen represented with X having lone pair of electron. Three lone pair of electrons are there on halogen. Only one set of lone pair of electrons are represented here. Okay, so you know that this lone pair of electron it can participate in resonance. Therefore, the ortho and para positions are more electron density, or we can say that it is a electron, it is ortho para directing group. Okay, if a halogen is present, if it is fluorine, chlorine, bromine, iodine, generally we can say because of the presence of lone pair of electron, it is ortho para directing group. Okay, so position 1, 2, 3, 4, 5, 6. Okay, at position 2, 4, 6, we expect an electrophilic attacks on ortho and para positions. But even the benzene, compared to the carbon present in the benzene ring, carbon halogen bond, we know that halogen is more electronegative. Therefore, there is a electron shift towards the sigma bonds of carbon halogen towards halogen. That means even it can be an ring deactivating. It deactivates the ring. Okay, so both present here. Okay, that is the peculiarity of halogens when it comes to the substituted aromatic compound. Halogens are orthopara directing as well as they are weakly deactivates the ring. Okay, so for both effects are there, but the attack on orthopara position it going to happen. That's why I put a smiley there. Okay, even though it deactivates the ring, possibility of attack of orthopara, or we can say halogens are orthopara directing groups. The resonance effect is due to the pi electron movement of p orbitals of carbon atoms in benzene ring, that is 2p orbitals, that we already seen many examples in my previous videos. The resonance stabilization of benzene, that is the delocalization of pi electrons. Delocalization of pi electrons present in the p orbital. Okay, p orbital, the dumbbell shaped orbital, that is actually 2p orbital of carbon. Okay, this I think this, what the statement it is understood. And among the halogens, if you compare the p orbital, the lone pair of electrons, the p orbital or the dumbbell shaped orbitals, it is in case of fluorine it is in 2p, in case of chlorine it is in 3p, in case of bromine it is 4p, in case of iodine it is 5p. Okay, so that also you can see, you can check the periodic table in which the atoms are. You can check the electronic configuration, then we can see that in case of fluorine it ends up with the 2p. Case of chlorine it ends up the outermost orbital it is 2p, 3p, 4p and 5p, like that. So when we compare with that of the benzene ring p orbital, that is carbon's p orbital, there is a size mismatch. Okay, so it's an important concept that you are not studied in your pre-university level. Okay, so orbital, the size mismatch affect the orthopara orientation. That is due to poor overlap of orbitals. That means the sidewise overlap of p orbitals, but 2p orbitals are smaller in size, 3p orbitals are bigger in size, 4p orbitals are further bigger, or 5p orbitals are even bigger in size. Therefore, the sidewise overlapping it is affecting. That means size mismatch is there. Therefore, we can see that it almost matches with the carbon's 2p, it matches with that of fluorine having 2p. But when it comes to chlorine, it is 3p. When it comes to bromine, it is 4p. When it comes to iodine, it is 5p. Therefore, you can guess or you can analyze how will be the rate of reaction if it is bromobenzene, if it is chlorobenzene, if it is iodobenzene. I think that is also understood. For the point, it is clear to you. The same sized p orbitals, if it is the more delocalization will be the more stability will be the more faster will be the reaction. Therefore, chlorine will comparatively chlorine will be chlorinated benzene or chlorobenzene reacts faster towards electrophilic substitution compared to bromine, compared to iodine as such. Okay, so in which the fluorine, if it is we already said that it is 2p orbitals of fluorine, it matches, there is no mismatch with the 2p orbitals of carbon present in the benzene ring, but fluorine is highly electronegative. Therefore, at ortho position it feels the electron withdrawal effect. Both ortho positions of the benzene ring, if fluorine is present as a substituent, it feels the electron withdrawing effect. Electron withdrawing effect means the ortho position electron density it got affected. That means at para position it is not affected, and it is also showing the resonance effect. Therefore, usually it gives the para position. That's why I took the example nitration of fluorobenzene. Okay, so this is fluorobenzene. Fluorobenzene, it can give nitration reaction, and the nitration reaction, the expected product is, I'm not stuck here. Okay, I'm just giving you time. Anyhow, you will pause the video or you pause the video and check. So here fluorine F is having one pair of electron, therefore ortho position and the para position having electron density. But fluorine is more electronegative than carbon. It is the smallest atom, therefore electron movement is towards the fluorine. That means these positions, and also we know that the inductive effect it diminishes after the third carbon atom, or the effect is very less when it goes to third carbon atom. Therefore, first carbon atom, second carbon atom, third carbon atom, fourth carbon atom, the effect, inductive effect, electron withdrawing effect, the electronegativity effect will not reach to this position, and that is also a para position. And para position, due to the resonance stabilization, it is activated. Therefore, we can expect a NO2 substituent or a nitration, or the NO2 group will be attached to the para position. Therefore, nitration of fluorobenzene usually, or most of the time, it will give para substituted or para nitro fluorobenzene. Okay, now orthopara and meta directing groups. Orthopara and meta directing group, conclusion of that. Orthopara directing strongly activating groups are O minus, NR2, NHR, NH2, OH. Moderately activating groups are NHCO and CH3, NHCOR, OCH3, OR. Okay. Weakly activating groups are OCOCR, OCOR, methyl group, ethyl group, alkyl group, phenyl group, as well as the vinyl group. CH double bond CR2, di-substituted. So it also activates. Okay, it supports, it pulls the electron density. Weakly deactivating group. Okay, anyhow, it is ortho para directing. That is what I explained. A special case, it deactivates the aromatic ring, but still it is ortho para directing. Now, meta directing strongly deactivating groups like NO2, NR3 plus positive charge on nitrogen, phosphorus R3 trialkyl phosphine, that is again positive charge on phosphorus, CF3, CCl3, etc. are strongly deactivating group. Moderately deactivating groups are cyanide, SO3H sulfonic acid group, CONH amide group, acid chloride group, ester group, COR alkyl ketone group, aldehyde group. Comparison or preferences of ring activating and deactivating effects. What are the preferences? When more than one substituent is present in aromatic nucleus, that means two di-substituent, then position of the incoming group, it is determined by the more activating group. Okay, so in taking the example, benzene ring containing NHCOCH3 as one of the substituent, CH3 as the other substituent. Now, which is more activating group? NH group or nitrogen is more activating group. So bromination, it will be giving the product towards the bromine, because CH3 group, alkyl group, its effect overcome by the effect of NH. Therefore, the ortho position electron density is more. Okay, this position to CH3, it is meta position, but for NHCOCH3, it is ortho position. Therefore, substitution will not take place to the meta position of the more electron donating group. Okay, it will go near to the ortho position to that group. That means mostly strongly activating substituent for the incoming group. So both are activating group only, but the most strongly activating substituent decides the position. Therefore, to that it is the ortho position. When the directing effects of two groups reinforce, that means both work together, the new substituent is attached to the position directed by both groups. Okay, taking the example of nitrotoluene, para-nitrotoluene on bromination. What is the expected product? NO2. Okay, what is the expected product? When the directing effects two groups reinforce, the new substituent is attached to the position directed by both groups. That is Br. Okay. In bromination of para-nitrotoluene, incoming Br group attaches ortho to CH3 and meta to NO2 group. So both are reinforced. One is activating, other one is deactivating, and both we know that deactivating group gives meta substituent and activating group gives ortho as well as para. Okay, so ortho para position is not free here. Okay, so to CH3, the para position already it is substituted. Therefore, this is ortho position to CH3 that is supporting our concept, and towards NO2 group this is meta position. Okay, therefore it is ortho para directing for CH3 and meta directing for NO2. Therefore, the expected substitution takes place there. There will be little or no substitution between groups that are meta to each other. Meta, they are meta to each other. Metaxylene. Okay, so nitration, CH3. Now, what is the meta position to both? This is ortho position, meta position. For the second CH3 group, ortho position, meta position. That means at meta position, no substitution for the meta position to each other. Both the CH3 group, that is the meta position, they're not at all possible. The nitro group, NO2 group cannot come to this particular position. What about the position 2? Okay, position 2, it is ortho position, but position 2 it is crowded. This CH3 group also there, this CH3 group also affect the, therefore it is little bit a steric hindrance is there. Therefore, the two position also not so preferred. Therefore, we can expect a NO2 substituent at a meta ortho position to one of the CH3 group. Therefore, in nitration of metaxylene, NO2 group is substituted ortho to one CH3 while it is para to. Okay, there is a space required here. It is not para to, para space to the other CH3 group rather than at position 2 to avoid crowding. Now, for substituents with opposite effects, the resonance effect overrides all other effects. Now, that example I'm taking hydroxyl substituted toluene, CBr to FeBrg, that is bromination reaction. Now, OH group, substituent with opposite effect, the resonance effect overrides all other effects. So both are electron activating, but they are on other side, opposite sides. Therefore, one group, that is OH group, it is electron donating with the resonance stabilization. CH3, it is electron donating through inductive effect. Therefore, inductive effect above that, resonance effect overrides. Therefore, Br substituent is takes place at the ortho position to hydroxyl group. Bromination of paracresol. Bromine is substituted, or I said hydroxyl toluene, that is not the correct name. We call it as a paracresol. The common name of this particular compound is paracresol. And bromine is substituted at position ortho to OH than at ortho to CH3, as OH is powerful activator due to resonance. Now, aromatic ring activating, that is donating substituent, it overpowers or overtakes an ring activating acceptor, ring deactivating, that is acceptor substituent or electron withdrawing substituent. So example, if I take, okay, NO2 is there, CH3 is there, NO2 is electron withdrawing, CH3 is electron donating. So which one we have to consider? We have to consider the electron activating or ring activating or electron donating. Okay, so you have to give more preference to CH3 group. when another substituent comes, so again nitration only. Okay, so the possible nitration possibilities are there at this position. Okay, the other positions here, ortho position also substituents possible, but it is near to NO2. The crowding effect is there, therefore NO2 will be there. Okay, so note it down. Anyhow, you can pause the video and write it down. Okay, if both the substituents are ring activating, resonance donor substituent overpowers a inductive or hyperconjugative donor substituents. That means, example, if I take one is having inductive effect, the other one is having a resonance effect. Okay, so resonance effect it takes already that given the example. Okay, so we are there. So in synthesis of a disubstituted benzene, also all these effects. Okay, so this one I think you can pause the video and note it down. It is already explained. Take another example. Okay, so when we go for a synthesis of a disubstituted aromatic compound, all these concepts are very important. Otherwise, we will end up with a wrong product. Okay, say example, the bromination of benzene followed by nitration. Benzene initially undergoing bromination reaction, then separating that brominated benzene, purifying it, then further it allowed to undergo nitration reaction. Okay, what is nitration reaction? What is halogenation reactions? That will be explaining in come next video. Okay, so taking example, bromination first. Okay, so we already know bromine can be attached to any of these carbon, 6 carbon. You'll get a bromobenzene. Now the bromobenzene on nitration, where we are expecting the nitration. Bromine is a ortho para directing. Therefore, more electron possibility is at ortho is also there, para is also there. But ortho position, due to the electron withdrawing inductive effect of bromine, para position is most suitable, or more yield is obtained with a para substitute. Therefore, para nitrobromobenzene. If you follow this reaction steps, the addition of the reagents, initially bromine added, then the product obtained, then nitrating will be getting para nitrobromobenzene. If we reverse this, if nitration of benzene is followed by bromination, initially nitrating, that means the benzene on nitrating mixture, okay, around 25 degrees Celsius, it gives nitrobenzene. Okay, so we got the nitrobenzene. Now nitrobenzene further we are making it to react with bromine in presence of FeBrg, bromination reaction. Nitrobenzene, nitro is a benzene deactivating group. Okay, so deactivating group means it will destabilizes the ortho para positions. Therefore, the bromine can attack the meta position. Okay, it is a meta directing group. Therefore, what we got a meta nitrobromobenzene. So almost the same type of reaction that we expected, but finally we end up with a different product. This is meta nitrobromobenzene, and when it was done by bromination first and then nitration of benzene, we got a para nitrobromobenzene. Okay, so two different products are obtained, and even if you compare the rate of reaction, whether the preparation of a para-nitrobenzene is easy or meta-nitrobenzene is easy, that you can explain as a comment under this description, or when you meet me, you can explain in detail why it is, which one will be the faster reaction comparatively, or practically when we do it in our lab, preparation of para-nitrobenzene is easy or meta-nitrobenzene is easy, you can get it easily, that you can try. Okay, so all these classes I'm uploading to my YouTube channel, My Intuition. Once again, I request you to subscribe if you are a new student to my classes, or my regular students. They already subscribed. I'm thankful to all of them. They are great us. I'm happy that you all subscribed. Okay, so please do subscribe my YouTube channel, like the videos, share the videos, share the information. It is not that much interesting as you watch many other YouTube videos, but still it is informative. It will be there in your brain throughout your career. Wherever you can apply it. So once again, I thank you for watching this video and have a nice day.